So it's a pleasure to be here. Let me start by offering my congratulations to Irfan and all the members of the new center. I'm definitely someone who can testify to the power of having a critical mass of a bunch of people much smarter than you around at all times. I'm very grateful for that, especially Michelle Deveray and Steve Gervin. You heard from Steve this morning. Michelle will be speaking tomorrow. I also know that tomorrow is supposed to be the main time where we're saying thank you and happy birthday to John Clark, but this is my moment at the podium, so I couldn't resist. As you've heard, John is really a founding father, the founding father perhaps of the field. For me, kind of personally, he's also a kindred soul who's obsessed with noise. Is that a nuisance? Can I understand that? Is it maybe even physics? And also I think John's really been, even though I've never had the pleasure of working directly with John, I've known him for many years, and for me, he's a model scientist to emulate. So this is a very random thing, maybe, to select from his enormous oeuvre. Even if you can't read it because it's a lousy reproduction, it's the table from Wellsted, Urbina, and Clark about 1 over F noise. It's sort of explaining all the many reasons why, as far as we can tell today, it's none of the above. And so why did this make an impression on me? Well, how many of us would have gone to all the work and all the detail to go through this? Perhaps you would have thought of some of these things and you would have discussed them in your group meeting or whatever, and there'd be a line in the paper that would say, well, we don't think it's any of the usual suspects. But I think, even in this case, it was we still don't understand 1 over F noise. Here he's presenting this really cogent, carefully argued thing that's explored all the possibilities, and this is a hallmark of his kind of science. And I think, why is that important? Well, because this is a great field to work in, and there's a lot of amazing things being done all around the world, and the results are very robust and so on. And where does that come from? It comes from the model set by the senior people in the field. So John, thank you for all of us, and especially also for me, for being a trailblazer and making this a great field to work in. Okay, so I'm going to start with a few personal, or maybe from the point of view of our team, general things about the state of play and where we probably are going, and then I'll, as time permits, give you some more specifics about some of these recent experiments on error correction. So I think we're at an important time. It's a tipping point. We're at the onset of scaling in this field. In the next few years, we're going to see at least interesting, maybe we don't know when we're going to have useful devices that will compute things we can't otherwise compute, but we're soon going to see interesting devices that have a complexity you can't simulate classically. The work is getting very technical and complicated and demanding, but I wanted to say, sort of echoing some comments that Hans made in his talk, this doesn't mean the science is over. The transition from a pure science discipline to an applied field is not a one-bit transition, and the science actually will never go away. What I think we're seeing, though, is that there needs to be more interactions of the kind that maybe this center can help foster here between different fields. It's not going to be just device physicists like me, but also systems engineers, information theorists, maybe even black hole theorists, and so on, to make this exciting new discipline. So where are we in a very global scale? Steve already flashed this diagram, but this is something that Michelle and I came up with to sort of show where we're going. So the idea is to build complexity and do more interesting things with quantum information. But remember, we want to build complexity in the sense of our quantum computing ability or the functionalities that we can do, not just in sort of brute force, how many balls can I juggle, how many physical objects do I need to make. And in the scheme of things, there are many important breakpoints here. The point of this slide really is to say that sort of when we wrote this paper and maybe sort of today, we're about here, where we can do many of these things like have coherent qubits, do algorithms, do QND measurements, and now we can actually address interesting questions like quantum error correction. That'll be the focus of what I talk about later. So there are, as has already been mentioned, many, many possible ways to make qubits. Many of them are very promising. I'm going to talk about superconducting circuits, and you'll hear a lot about those over the rest of this meeting, I'm sure. So there are many reasons we think this is a very powerful technology, right? So superconductivity, nature's been kind. Josephson junctions are really good. We can make surprisingly good devices. The fact that these things are all just under electronic control, you can mass produce them, you can make devices with differing properties, many elements on a chip. These are all very nice. And now there's this really powerful ability with these microwave signals to do the control, the measurement, the entanglement, and so on. And one reason we're very optimistic and very bullish about this field is this following chart, which again, Steve already showed, but maybe I'll just make a couple of comments about it, right? So for us, as you heard when the field started, of course, the question was, can an object like this even have energy levels? And that was answered in the affirmative by John and his colleagues some 30 years ago. But then could it ever be really coherent enough that you would do anything? And so this progression has been quite dramatic. I think now most people would say over the last few years we've crossed past the point of having enough coherence that in principle one should be able to make large-scale devices and do error correction. And also, right, it hasn't rolled over yet. So that means we haven't seen the limit. So hopefully we can keep satisfying Girvin's law of ever wanting more and more coherence. And there's been really amazing progress that's not maybe as easy to put on one simple line chart in all sorts of other aspects of these technologies, including especially progress in measurement. So this shows from the lab of my collaborator and colleague Michel Devereux, trace of individual quantum jumps. His team has been developing these parametric amplifiers for many, many years, even back to the days when Irfan was a postdoc. And the first example, of course, of these kind of jumps were done here in Irfan's lab at Berkeley. And so, what does this mean? Well, it means now that you can measure the state of a qubit, and more importantly, the state of one qubit in some collection in order to do error correction in times of a few hundred nanoseconds with very high fidelity using these kind of devices. And this is one example also of something that now gets to be a semi-commodity item. We use these things in quantities of dozens in our lab, and they are now available from that small company that was listed in the disclosure on the first slide with 12-week delivery time. So, for educational institutions, it's tax-free, that's right. So you can read the data sheet on the website. So I'm not going to go through all these questions, but again, sort of building on this theme of it's getting more serious, the technology is advancing, but there's still lots of science, and of course, every time the technology advances, you have new science questions you can ask and start to answer. Questions like what's the best architecture? What is the best way to do error correction? This is one which hasn't been mentioned. What are the first simulations you will do and what's going to really be required for that? Those are interesting questions. And some of these now, like the architecture and the quantum error correction, become things which are not just theoretical questions, which they've been up till now, but something where we can have a practical discussion about them. And so my real hope is that we're going to see even faster progress now in the field as the gap between sort of information theory and practice in the lab starts to merge and maybe even overlap. So I want to give you two examples of this from our particular team's work now that kind of illustrate this idea that there are new ideas that you can come up with based on an understanding of the technology and also new paths forward that are worth investigating. So you'll probably hear more about this also from Chris Monroe later on. Something we've been now enamored of for several years at Yale is this idea of the so-called modular architecture for quantum computing. And I'll sort of explain this cartoon a bit in a minute. If you like, it's a networked quantum computer, or it's a quantum internet, as was pointed out and championed by Jeff Kimball, with various repeater stations that are connected together and entangled. And what we like about it a lot is that this seems like a really good way to bite into the complexity of building larger quantum systems. It's basically a way to take standardized subunits and wire them together in a quantum way into a larger and more powerful and more complicated whole. So we don't have to build one monolithic device. So what are the ingredients in this? You need the so-called modules. So these are small quantum systems. Here I'm sort of trying to cartoonishly illustrate 2 qubits, but they need to be more complicated than that. They need to have the ability to do useful things within, like, for example, run error correction so that the information in each of the modules essentially represents a logical qubit, and then they can be networked together to do algorithms or operations between these modules. And so, basically what that should be is the largest quantum computer you can currently build and do it reliably and mass produce it, okay? And then the idea is you make the complexity by stacking many of these modules and coupling them together. And the way you can couple them together is using, for example, a router. So now, if you have the ability to make and break connections here, you can decide, as your algorithm requires, whether I want to do entangling gates between this module and this module, or between this pair of modules, and so on. And then you need some way to do this entanglement. You have to make bell pairs between the modules. And one way to do that is, for example, using these kinds of single photon detectors. So this could be an internet where the modules are in different physical locations. But for us, for example, this whole thing can fit inside one cryostat, and the modules might be little bricks containing 10 or 20 qubits, size of your fist or smaller, and you can have many, many of those together and do all of this in the microwave domain. You'll hear about ways to do it in the optical domain, and maybe one day we'll have, modulars of modulars where you have interconnects that are optical between longer haul stations in your network or the like. And so, again, I say this is a practical thing. So, for example, my colleague Michel Devray's group, again, has actually been able to do the entanglement of 2 such modules in a dilution refrigerator using these microwave techniques. And so, talk about macroscopic quantum effects. There's multiple sort of literal blocks that you can take apart and test separately, and you can connect them together. And again, with these kind of microwave measurement techniques, they were able to make an entangled state between these 2 things. So not only are they large, they're separable, not in the actual experiment, but they're separable in the sense they were taken apart and cooled down separately to calibrate them in the beginning. And this is, again, one of the powers of this superconducting circuits is very strong interactions are possible. In fact, even the interactions between these modules can be done in sort of sub-microsecond timescales in this kind of technology. The strongly interacting superconducting qubits allow you to do very fast gates and fast operations. Okay, so now let's talk a little bit about error correction, and I'll hopefully deliver some more of the things that others were promising I would talk about. So there are several approaches to doing quantum error correction. The sort of original one from Shor, although here I'm showing the Steen code, is the so-called stabilizer. There are also these approaches like the surface code. And if you just sort of start looking at this and saying, well, okay, this is basically what's required here to build a logical qubit. So if we do a resource count for making just one layer of error correction, and let's just say we want to do memory, we want to make a state that will live longer. This is some notional count of the number of parts and the number of operations and things you need to do. And as you've heard, this is not impossible to do now. Maybe 5 years ago we would have said, oh, who knows, can we ever do that? But again, these are ideas that are very beautiful, but are sort of theoretically motivated, okay? If we look at them, there's sort of a chicken-egg problem here. We need to get error correction to work so we can scale up and make bigger and more complicated quantum computers. But on the other hand, we really have to do a lot of physical scaling of the parts before we can actually attempt error correction. And you wonder, am I just going to be running faster than, is the goal running away from me faster than I can manage to run? And so something that we've been thinking about is an idea we call hardware efficiency. So let's try to do this function, or an approximation, a good approximation to that function, with the fewest number of moving parts and the smallest experimental effort that's required. And the answer, in terms of making a quantum error correctable memory, is this thing called the cat code. So we'll use our best object, which is a microwave cavity. It can store multiple photons, as Steve was describing in his talk. So it's a way to redundantly encode quantum information and to, in principle, correct the errors. And in this code, the dominant thing that goes wrong in our cavities is that the Q is only 10 to the 8. That is to say, it lives for a millisecond, but it loses a photon if I store one photon in it every few milliseconds. And it turns out I can detect that error in a very parsimonious way, very economical way, with just a single ancilla qubit and a single readout. So here's the way this encoding scheme and this idea works. Again, we're going to use a non-standard object from the quantum computing theory side of things. We're going to use an oscillator. It's a continuous variable system, and so we're going to see a lot of things where we have these kind of Wigner functions here, which are plotted as a function of position and momentum of the oscillator. It's a continuous variable system. And the kind of obvious encoding is, well, let's have logical 0 be no photons present, and logical 1 will be 1 photon present. And then I have various states that are superpositions of those, which would correspond to the other values my quantum bit can take on, the other locations on this block sphere. Now, the problem here is this is not error correctable. It might be a good passive quantum memory, but I don't know how to error correct it, because if I have photon loss, 1 goes to 0, 0 goes away, and well, so I can't do anything. I need to have some redundancy. I need to use multiple photons to encode the information. And the easiest way to do that is to use a coherent state. That's easy to make. Just give the oscillator a kick. And now, if a photon loss occurs, it doesn't make these two states exactly the same. I can still distinguish the two coherent states if they have a few photons, even after the loss of 1. But that's still not enough to do error correction. I need to know if something's happened. And so the trick here comes from looking at these kinds of states. So this state, alpha plus minus alpha, or the superposition of plus x and minus x, is something which has, for example, many photons. You're not sure the photon number, but you know the photon number is even. And if I use those states like this, or this one, which is also even in photon number, it's the superposition of plus p and minus p, I can have a logical block sphere within this many photon space where all of the states that are allowed computationally have the red in the center of the candy. They are all even parity. And so this parity will be the syndrome we'll detect. Of course, when we lose a photon, it's going to change from even to odd, and we'll know. So again, these are the code words. We'll put them together. We'll see lots and lots of these fourfold symmetric things, these 4-component cats. And this is a way to store and efficiently error correct. So here's what's going to happen. We put some state on the block sphere into this thing. It'll be some superposition of the two cats. Most of them will look like this with 4 components. And at some point in time, after we've stored the information, a bad thing occurs. The qubit, the logical qubit, interacts with the environment. At some random time, we don't know when, a photon is lost, or the environment, someone applies the operator A. And the information is transformed, but in a way that I know. So if I knew that the error had occurred, it wouldn't be an error, or I could fix it. Now, more than 1 loss might occur. 3 losses might occur. It turns out in this code word, you're an eigenstate of a to the 4th, so you come back around if there are exactly 4 errors. Now, the other thing that happens in this cavity is your coherent states start with some amplitude, and they decay. At infinite time, you will find the cavity in vacuum. But that's actually a sort of easier thing to correct in some sense. It's actually a deterministic shrinking or reduction of the energy. And there are ways to correct that, and I believe Michelle's going to talk about really interesting other ways of using these cats and of repumping the cats to maintain their energy for long times tomorrow. So let me show you now, in the time remaining, that we can put all this together and actually demonstrate in the lab quantum error correction that works, that gets you toward the goal of actually preserving your information and making the lifetime longer. So again, it's a simple apparatus. It's 2 of these microwave cavities. One is just used for the readout, and 1 transmon ancilla. It's got one of the standard Hamiltonians we use. We have a fast amplifier so that we can measure with very high fidelity the state of the transmon, but of course not directly the state of the cavity. And what we're going to do now is we're going to take a bit of quantum information. So we have to do process tomography. We take all of these 6 different points on the block sphere, and we store them one at a time in the system. And we encode in this 4-component cat. Then we wait for some amount of time. The environment does its nasty things. But at the same time, we monitor and we measure intermittently, is the photon number even or odd? That's our syndrome. Are you even or odd? Even or odd? And then depending on how many jumps we think we've seen, how many times has it flipped from even to odd, there's a prescription about different ways we need to decode the information and then apply a transformation on the information to correct. And then in the end, the goal is to do something that looks like this. If you are an expert, you know this is process tomography, and this is what the ideal process tomography of the most trivial function looks like. This is do nothing or identity, and the idea is to have that bar be 1, and then you're really making a good memory. So now I made it all sound very simple. This diagram I'm not going to go through in detail, but it's to give you an idea also of the kind of complexity of things that people in the field can do and must do today. So even though it's a simple piece of hardware, now we're going to do something pretty complicated. We have to store, encode, monitor this syndrome. There's going to be a trajectory in which, following successive measurements, we either do or don't get a certain answer. And of course, we can't know what's happening all along, or we're going to decohere the system and destroy it. But what we can do is this kind of debugger view. We can insert a breakpoint here, and we store our qubit, and we look to see if it's encoded correctly, and you can go measure, and that's the experimentally measured Wigner function of the logical qubit as it's just been encoded. And here I'm just going to show you 2 passes of running the error correction. We can do 10, 20, 100 passes because this is all done under the control of a real-time FPGA system that took a lot of development. And actually also, each of these little blocks here is representing a function. Inside there are several pulses. Each of these things takes a microsecond, and some of them include actual measurements and so on. And so when you do the measurement, you can, the controller will decide has an error occurred or not, and you get different things. You see it's red or blue, and the controller's actually following and seeing whether or not an error has occurred. If you go 2 steps of the error correction, of course, you might have said, no, neither time there was an error, or there could have been 1 error, but it's different depending on whether first there was an error or second there was an error, and all of that. And then you can basically take these states and combine them and realign them and look at what comes out. And so the amazing thing here is we actually reached the first time what we call break even, where we're running the error correction is giving us back more coherence, more information than what we put in. And I don't think that's actually been done in any technology, in any system so far. So, and we're going to start by comparing to the worst thing in the system, which is the standard superconducting qubit, the transmon. So, if we store information even after a few microseconds, and then, if I run it forward 100 microseconds, you see everything is kind of collapsing, and the transmon's going to its ground state, and there's none of this information left. Now, if we store in the cat, but we don't use error correction, of course, the information decays as well. And here it's decaying more slowly because basically our cavity, the memory, is already physically a better qubit than the transmon ancilla. But now the really exciting thing is if we put it in and we turn on the error correction and we use this information, the knowledge of when or how many errors have occurred, it's not perfect. There's still a shrinking, but I hope you can see that this is bigger than that one. It's closer to a pure state. There's some more information left. And if you want to compare times, here's sort of the decay of the information versus time, just storing in a physical transmon. The best physical qubit is this dashed line here, which is storing 0 or 1 photons in the cavity. The yellow line is storing in the cat, but not doing the error correction. And you see there's a sort of dirty secret here. Error correction makes things worse before it makes them better. The redundancy you introduce means that errors happen more quickly. And here what we were able to do with the error correction is get back all of that overhead plus just a little. So it's just the beginning of doing error correction. Don't want to say it's all over. But again, sort of, it's an applied field, or what does this tell us about what we want to do going forward? So we look at a budget for this whole system, this error correcting system. And again, I'm not going to go through the details, but there are many things that can go wrong. And the interesting thing, which I didn't expect at the beginning, is that many of the things like the fidelity of the readout of your transmon, that just didn't matter at all in this experiment. It turns out actually the dominant thing is forward propagation of errors, or the fact that even though this is a first order error correcting code and it's working correctly, and it's compensating the dominant decoherence due to the environment, it's not doing that measurement and correction in a fault tolerant way. So the act of measuring can introduce some errors with a very low probability, but enough that it limits your performance. And in fact, the performance is exactly what it should have been. And you'll find the same thing if people go and build the Steam code. You will not originally do that 13-qubit experiment in a fault-tolerant way, and you will be limited by the same kinds of effects, although there's even more ways it can be non-fault tolerant. So there's a prescription for how to fix that. The information theorists know how to build a fault-tolerant quantum error-corrected memory. It's pretty bulky, and there are shortcuts. And hopefully we'll see those coming out of the lab soon. OK, so in the 1 seconds left, let me just flash really quickly 2 more results. So that's just doing an error-corrected memory. Can you use these cats for anything else? And the answer is, I assert, yes. You have to be able to manipulate these logical qubits, and eventually you want to be able to do gates, do information processing on them. You want to do entangling operations between them. And again, we can start to make those kinds of things practical questions in the lab. So to manipulate that 4-component cat, you can maybe understand we have to move around or change the state of many photons in the box at once. Same thing happens in any kind of logical qubit. Doing a gate on a single qubit is much more complicated than just doing a pi/2 pulse on a physical qubit. So here, just to sort of show off, we built something where we're going to go directly from vacuum to 6 photons all at once. And what we do is we put in the coupled transmon cavity system. We measure its Hamiltonian very carefully, and we say, we want to just go there. Please compile that operation for me. And we throw it into a standard technique of optimal control theory using grape, and you get out some crazy pair of waveforms you're supposed to play. The system's supposed to do some trajectory like that. That's actually data. And indeed, you get a very good representation of a 6-photon Fock state. You can go directly from 0 to 6, OK? And what we can then also do is manipulations on these 4-component cats. And now this corresponds to taking a logical qubit and doing 2 successive pi/2 rotations. We can do hundreds of these operations in a row. Again, they're all compiled and loaded into your waveform generator. And already the fidelity of doing that is 99% in this system. And we know why it's only 99%. And in principle, how to make it better. And yeah, now I'm really out of time. You can also do things with multiple cats and multiple cavities. We can make not just this kind of a cat, but this kind of a cat, which is, if you like, the analog of a bell pair for this kind of logical qubit. And there's the data showing that it actually works. And what it means here is now we can already make a particular entangled state of this kind of system of 2 modes. And we're sort of manipulating now in a Hilbert space of 150 to 200 degrees dimension. So that's essentially the equivalent of a logical byte. All right? So where are we on this scheme of things? Well, yeah, it was sort of 1998 or so that the first operations on single qubits could be done. But of course, the beginning was the 80s and MQT here. First algorithms were done in 2008, 2009, jumps in 2011 or 2012. This doesn't mean it's over. Of course, all of these things need to get better, and there's lots and lots of great science and great work being done on all of these. The first experiment was late 2015 or so in our lab, and I'm showing you that we are manipulating single logical qubits. So I don't know, are we going to see algorithms between logical qubits in 2017 or something like that? But I think the prospects are very good, and you can see that the pace of progress is accelerating. So I think I've now indulged everyone's patience and the chairman's patience as well. So why don't I just leave you with those things and say, once again, congratulations on the launch of this exciting new center, and thank you very much, Mr. Chairman.
Well, thank you, Rob, for that great talk. And are there questions or comments, please? Yes.
So the thing that concerns me, this is really cool, but you're protecting against one kind of error. And if you compare with the Steam code, for instance, which protects against 2 different non-commuting kinds of error, do you have any idea how the complexity, clock cycle, and other measures of resources for this experiment would increase if you protect it against two non-commuting kinds of error?
Right. So it's a good question. I mean, I think my first point was eventually we need to correct for all of the errors that we care about or that are going to happen enough that it gets in the way of doing the calculation you want to do. And you should start by correcting the ones which are the most important. So for example, a problem with transmons is you really need to do the Steen code or the surface code because they typically have bit flips and phase flips, or they have T1, and I don't know of a shortcut that's analogous to this. Okay? But as Steve sort of mentioned in his talk, we've now understood, I mean, it's great to do these experiments and then it leads to new theoretical insights and more ideas, you see new things open up. So there are now a lot of ideas about how to use these bosonic codes, and with adding some complexity, which again, you might not have even considered doing because you didn't have the tools beforehand, you can add a few more photons or go to a slightly different code word that will protect you against this dominant error and the next leading order error, and so on. And I think that will double the complexity if we want to add one more error. So I don't know, I don't think we understand yet what the errors actually are in the hierarchy, and we don't understand or have a complete scaling map of how this is all going to go. But I think the point I'm trying to make is it might be a little easier to scale these things than everybody thinks.
We have time for one more short question.
David's got one.
Yes.
So you mentioned that you mentioned that if the error correction is not done in a fault-tolerant way, the first thing that happens is that you lose in terms of coherence time. I guess my recollection was that also in Irfan's group there was work in making a very long-lasting memory. Can you comment on whether this approach lends itself to that as well?
Let's see. So there are various functions you might want to do. So first of all, you could say I want to stabilize a state. Yeah. Just a state. Stabilizing the ground state's easy. Stabilizing a different state is harder.
I see it. Unknown
this
state.
is actually stabilizing an unknown state or a full bit of quantum information. And then this is a harder thing to do. And so maybe there's more stages in this chart than we included, and so on. Stabilizing a state or any state you choose, which has been done here, is great, and it's a useful function. But stabilizing a coherence is an even harder thing. Now stabilizing, doing a fault-tolerant gate between them is an even higher order function. So, yeah.
Okay, let's thank Rob one more time.